Okay. And okay, seems to be working. Hello. Okay. Yeah. So any question from this time? This time we go over quite a few concepts. So we go over I think the biggest concept we had is the direct product and orthogonal complement. And we have a very good example of those by the column space. So basically a row space of matrix and null space. We see the orthogonal complement and there's a direct sum into this whole Rn space. And we are talking about matrix A that's n by n. And so it's a mapping from Rn to Rn. Then we see we can then we can decompose Rn into this r-dimensional columns of AOT. So column space of AOT, basically the row space of A. And then so this is dimension R equal to the rank of A, and so those R dimension will map to another R dimension in the into the column space inside this Rn. And in those two blue space one by one. And then there is a HR null space here inside Rn, which is just mapping into basically nothing equal to map into 0. And this is dimension n by n. Okay, so that's about matrices. And then we talk about solving those least square problem. And that's when you want to solve A is equal to B, but this is inconsistent. So you cannot find X that actually satisfies this equation. So instead, you want to minimize the error, that's the difference between B and the AX you found. Okay. So you want to minimize this Rx as a norm of this, and this is a vector, so you want to minimize the norm of this vector. And so basically you want to minimize Rx squared, and we have a lot of derivation, and in the end, what we found is that we want to solve this normal equation. So instead of Ax equal to B, you want to solve ATAX equal to ATB. And give a whole bunch of examples of solving this, and they see that well, a lot of time this thing has so if A has 4 rank, then then this thing has a unique solution. And if not, then ATA has some null space, and you have more than one solution. And we give a few examples that has unique solution, and we also see that all these correspond to actually fitting a whole bunch of lines with with the best possible. Fitting a whole bunch of points with the best possible line, or fitting with them with a quadratic equation. Okay. So you can find that's not a quadratic. Okay, so this is a quadratic equation example. Okay. And yeah, but the bottom line is you want to solve ATAX equal to ATP. Okay, so that's quick review, and then let's go back to more mathematical thing. Today we want to talk about inner product spaces. So this is a bit funny because of the way we organize things. So the concept here you basically all know. We're going to talk about orthogonal and inner product and Cauchy Schwarz, etc. But we have been talking about those all in Rn, but now we are going to do an abstract version of them. So we are now assuming our vector space is not Rn. We are assuming our vector space is just a linear vector space as before, but now with this inner product structure defined on it. And so we are going to rederive everything, not in terms of what we know in Rn, not in terms of what we know about inner product in Rn, but just from the inner product operation that defined here. So yeah, so we are going to do everything once again, but in a very abstract sense. We are going to derive everything, saying that you only need to have an inner product satisfy those properties. Okay. So what are the inner product in abstract space? Okay. So inner product. Okay. And once again, we are in real number, and at the very end, we will have a complex inner product version. Okay. But that's not in a book. That's like something extra. But anyway, we have a real number as our scalar right now. So inner product is this kind of operation. So it's really like the operation in Rn. So you take two vectors in your vector space, and this operation will give you a real number. Okay, so you take two vectors and they give you a scalar. And okay, so in Rn we define this explicitly as sum of x1 x2 plus as the sum of x1 x1 y1 x2 y2 etc. But now this is just some abstract thing, and we say, well, you take two vectors, you should have some way to find some number. Okay. And but they still need to satisfy three basic properties. Okay. So first property, it need to be if you inner product a vector with itself, it need to be greater or equal to 0, and equal to 0 only when a vector is 0 vector. And then the second property is kind of symmetric. So x inner product y equal to y inner product with x. Okay. So it's symmetric in the two arguments. And then finally, it needs to be linear. Okay. And finally, it needs to be linear. So alpha x plus beta y inner product with z equal to alpha x inner product with z plus beta y inner product with z. Okay. So I guess we didn't explicitly show those, but you can easily check that those three are all true for the inner product we define on Rn. Okay. Yeah, pretty easily check that. Okay. And if a vector space has an inner product that satisfies all those three definite, then it's called the inner product space. So what we're saying here is a vector space does not necessarily have the inner product on it, but obviously Rn has it, and we are now going to study a vector space with inner product on it. Okay. And so some example of it. So first is once again our Rn. So our Rn inner product is defined as this x transpose times y. Okay, so I guess we can check these three. Okay, so let's write a little more here. So this thing is some I, xi, yi. Okay. Maybe let's write a little more. Easy. Okay, yeah. So it's equal to some. I want to write this. So this is, as we say, x1 y1 plus x2 y2 plus x yn. And so property 1. So if x equal y, then x equal to y. Yeah, x equal to y. Then this thing is x1 squared plus x2 squared plus xn squared. So this thing is obviously greater or equal to 0, and x is equal to 0 only if all those are 0. And xy equal to yx, that's just this thing doesn't care the order between xy. So those are all scalars. So x1 y1 equal to y1 x1 etc. So x inner product y will equal to y inner product with x. And if x equal to so you have I guess x equal to alpha x1 plus beta x2, then every over the coefficient will have this alpha plus beta, and this scalar multiplication is linear, and so everything is linear. Okay, and so that's one inner product. And okay, so we don't actually have too interesting example here, but anyway, we have a very similar example here. So we can also define inner product between between two matrices. So remember we say for matrix, so for n by n dimension matrix, we can also think it as a vector space, and So we basically think this as we basically map this into Rmn, and yeah, so we have a similar inner product. Inner product is we just sum over. So we just multiply. So we have two matrices that's both in A and B, both in n by n. So they are n by n matrix A, n by n matrix A, and n by n matrix B. And we define inner product by just saying we multiply the elements together and summing over all of them. And obviously this is the inner product because this is like an n-dimensional vector. Okay, but obviously you can also define weirder inner product in more abstract spaces. For example, the book has some example on even dimensional space, like the function space, linear space of functions, etc. But let's skip that for now. And so now let's derive more property on inner product space. Okay. And first is we can define we can define a length of a vector. We are inner product, so length is something positive and the inner product is positive. So that's nice. So inner product is positive and then we take a square root is still positive and we call it length. Oh sorry, inner product is positive when you are inner product two things with itself. Okay. So it's the inner product with yourself is positive and we take a square root, that's the length of the vector. Okay. And now we back to the orthogonal thing that we've been talking about. Okay. So yeah. So two vectors are orthogonal, we define it when their inner product is 0. Okay. And then we have our first theorem, that's the Pythagorean law on whatever arbitrary vector space. And it says that if you have two orthogonal vectors, then u and v, and then u plus v squared equal to u squared plus v squared. Okay? No, u, v, so it's like this. U and v, and so this length square equal to this length square plus length square. And yeah, so we don't need any Rn structure to to derive this. So we can see that we derive this by just the inner product property. So all those length square are defined by inner product. Okay, and so non square length square is the inner product between u plus v and u plus v. Okay. And okay, so here we have something that we didn't say, and I guess we can say it here. So so here we use the property that if you have an x inner product with alpha y plus beta z, this is equal to alpha x inner product with y plus the beta x inner product with z. And this thing you need to derive by saying so this thing equal to, so you need a symmetric of the inner product is equal to alpha y plus beta z inner product with x. And then you can use the linearity on first argument and go into this and swap it back. Okay. And yeah, because in our definition we also only say the inner product is linear in first argument. So if it is linear combination on second argument, then you need to swap it to use symmetry, use the symmetry between arguments, swap to it to first, and use linearity, then swap the xy back, yx back to xy, etc. But anyway, so we know inner product is linear in both the first argument and the second argument. So this is the inner product between u and v. Okay, yeah. So this is u plus v and u plus v. So it's linear in first argument, and so it's u inner product u plus v, and the v inner product is u plus v. And then as we say, it's also linear in second argument. So it's u inner product v U inner product is U and U inner product V. Then V inner product is U, V inner product is V. Okay. And so now we have our two terms, U square and V square. Then we use the symmetric of the inner product. So V inner product is U equal to U inner product V. So it's twice U inner product is V. But then finally we use the orthogonal. We know that the orthogonal vector, the inner product is 0. So this term is 0, then it's just a U squared plus V squared. Okay? Yeah. So this is the Pythagorean law for general inner product space. Any question? Okay. And if not, then we define something that we also defined before. That's the orthogonal projection. Okay. So yeah. So this is basically what we do in Rn, but now we write the inner product in the general form. So we also just okay. But, so basically we mimic what we had in Rn, and we just define the orthogonal projection here. So once again, we still think we have. Let's see. So let's say this one is V. Let's say we have a V here and U here. Okay. Try to draw a little better. U here and V here. And so what we want is we want the orthogonal projection here. Okay. So we want to say U equal to some P vector and plus some U minus P. Okay. So we have the orthogonal projection and well yeah. And we kind of think this is weird. Okay. So like the intuition is that the inner product is U length V length times cosine theta, but we haven't defined theta here, so this is just an intuition. So, but for the okay, so this is beautiful construction, but for your memory, so remember in the Rn case, we say the angle here is theta. And this inner product is like U length V length cosine theta. So then this length of P here. So length of P here is alpha is U cosine theta. So it's UV inner product divided by the V length. Okay. Yeah. Anyway, here we basically took those as the definition. So those are not derivation here. Here we just define the scalar projection and the vector projection of a vector onto another vector as those things. So the scalar projection, which is the length of this projection, is the U inner product with V, then divided by the length of V. Okay, and then the vector projection is actually this vector here. So it's alpha times the unit vector in V direction. So alpha times V divided by V length. And then we can do a little more. So alpha is the inner product between UV divided by V, then we have a V divided by V length. And then this is UV inner product and V length squared times V. So it's UV inner product divided by VV inner product times V. So yeah, so those are similar to what the definition we had in Rn. Okay. And then we still have a similar thing. Okay, so our definition is this, and then now we want to prove something that this also makes sense as before. So basically, what we want is, well, if it is orthogonal projection, then we want is U minus P and P to be orthogonal, right? So because this is orthogonal projection, that's the thing we want. Okay. We want that if we define the P this way, then P and U minus P are orthogonal. Okay. 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 And also we want to say if u equal to p, so from this picture you want to say, so if u equal to p, then u lies on this v line. Okay. Okay, so let's see the proof to make sure that the orthogonal projection is actually what we think they are. So u minus p and p are orthogonal. Okay. We do this in a funny way. Okay. So yeah. So basically we want to check whether inner product with u minus p and p. So yeah. So inner product with u minus p and p, then it's the inner product between up minus the inner product between pp. Okay. And then we do those two calculations up here. So inner product between p and p, where we write down write down the definition. So pp inner product is alpha b divided by b, alpha b divided by b, and so that's this. So this alpha divided by v known is alpha divided by v known is just a scalar, so it's a scalar part square, and then the v inner product. And so here we have alpha square and the v known square, but we know v known square is the v inner product, so it's cancel out its alpha square. And so this term is alpha square, and what about the up inner product? Okay. And this is anticipated, right? Because, because we know the length of p is alpha. That's how we define it. Okay. So length of p is alpha as we expected. Then we need to prove the inner product between u and p is alpha square. So inner product between u and p, and once again write out. So u and p we write it in this form. So it's this form. U inner product, v inner product, v. Okay. So u inner product and v inner product, those are scalar and v. So the LNC, the actual vector inner product is another uv, so another uv inner product. Okay. So this is unity inner product squared divided by v known square. And that's alpha squared because alpha is u inner product divided by v known. Okay. So yeah, so you see that this check out u minus p inner product with p equal to 0, and that means they are orthogonal. Okay, any questions so far? Okay, so yeah. So you see that those actually define orthogonal projection because the projective part and these two equations actually define orthogonal projection because the projective part and the remaining part are orthogonal. And let's also see that this vector equal to its orthogonal projection if only if it is on a line, on this v line. And okay, so it's pretty easy. So the if part, if it actually lie on this line, then then orthogonal projection we go to, so so if u actually lies on line, so it's on beta times this v, and we just plug in the equation. So p once again is u inner product with v divided by v inner product with v times v vector, then is u become beta v. So beta v inner product with v divided by v inner product v times v. So it's and so we take out beta, then those two inner product cancel out. So it's beta v and it equal to u. Okay, so yeah, so this trick. So p actually equal to u, and when p equal to u, then u equal to alpha times v divided by equal to p equal to alpha times v divided by this v known, and then we can just say p beta equal to this alpha divided by v known. So we see that u is some scalar times v. Okay, and then we go to next thing to prove Cauchy-Schwarz inequality. So we actually didn't prove this in Han, and now let's keep proving this more general case. Okay, and so the Cauchy-Schwarz inequality says that the norm of UV inner product is less than the norm U norm V. Okay. And the equality holds if only if UV are linearly dependent. Okay. And I guess we didn't have the full proof. We only proved the equality part, but you can see. But anyway, let's see the first part. So let's see the inequality. So to prove this, we use the orthogonal projection that we've been talking about. So let's see the orthogonal projection first. Let's write this down once again. So we have V here, we have U here, and we think we have orthogonal projection P here, and this is U minus P. Okay, so we think about this orthogonal projection P. Yeah. And so because from what we just proved, U, P, and U minus P are orthogonal. And by the Pythagorean rule, we have U squared equal to P squared plus U minus P squared. Okay, we use this orthogonal projection. And okay, so now we do our inner product thing. Okay, so now we can talk about our inner product by the definition of orthogonal projection. So the length of P square is alpha square, and that's the inner product square divided by the length of V square. Yeah, because the alpha equal to this thing, and this is alpha square, and this is alpha square. Okay, and so this is P square, and the other then, but P square also equal to from here U square minus this U minus P norm square. And then we are basically done. So now we multiply V square to this side. So then we have UV inner product square is equal to this U square V square, U norm square V norm square. So this is basically a term we want, minus another term that's U minus P square times V norm square. Okay. And I guess yeah. Okay. So minus U minus P square and V square, and but this term is greater or equal to 0 because all the norm are greater or equal to 0, and so this is just less or equal to U square V square. And so you see in those two things, this is basically what we want, right? Yeah. So let's just highlight this a little bit. But so this part is what we want. We have U square UV inner product square less than U norm square V norm square, and you just take a square root of it, then you get this thing. Okay. And then from here, we also see the equality equation. So equality, so equality only happens when this term is 0, right? So equal to 0 if and only if equality. And this thing equal to 0, well, basically you need V equal to 0 or U minus P equal to 0. And that means, so, okay. I guess if V equal to 0, then U is obviously linearly dependent on V. That's like a singular case. And if V not equal to 0, then U minus P equal to 0. Then we know that's the U lies on V line case that we just proved. And we know that in that case, U will be some multiple of V. Okay. And I guess we have been sloppy in our proof, we didn't. Yeah, okay, so this is when the V not equal to 0 case. Yeah. Oh, yeah. So in all the orthogonal projection, we are being a little sloppy. We didn't say that, but it's written here, so v need to be not equal to 0 because obviously you cannot project onto something 0. Okay, and we have been dividing the norm v, so v norm cannot be 0. Okay, so that's the Cauchy-Schwarz. We have a very general proof of Cauchy-Schwarz. And then since we have Cauchy-Schwarz, just like when we were in Rn, that's n bigger than 3, we can now define the angle theta between between two vectors. Although we have been kind of cheating and say that we got the intuition of our orthogonal projection from this theta, but anyway, now we can formally define theta because we know this uni uv inner product divided by u norm v norm is some number between -1 and 1, and so we can think this number as cosine theta. And yeah, so we basically take a cosine of this number, and we now know the angle between those two vectors, or we define the angle as a cosine of this number. Okay, so yeah, this is Cauchy-Schwarz. The proof is okay. Cauchy-Schwarz inequality, very useful. Okay. And no question, then let's keep going. And now we have something a little confusing. Okay. We have been talking about those are known, right? And because we cannot do this in reverse order. So now, so what are we doing? So we kind of we have been talking about things by a special case, then try to generalize everything. So what we have been doing up to now is, so we were talking about everything in Rn before, then we know that we have this very nice concept of inner product in Rn, and we try to generalize this to general inner product space. And the next thing we do is, we know that in general inner product space we have this very nice definition of norm, which is norm square equal to the inner product of vector itself. And what we want to do is, now we want to generalize the idea of norm. Okay. So it's an even looser definition, so we can define a norm on a vector space without it even have an inner product. So we say a vector space is a non-linear space if it has this norm defined on it. Okay. And norm is it's even simpler structure than the inner product. So it just every vector can have a norm on it. Okay. So it's basically a function from a vector to a scalar, and we didn't distinguish the notation here yet. So we write this double line, double line, and have our vector inside. And no need to satisfy this 3 property, so it's a greater or equal to 0. And equality hold if only if the vector is 0. So the norm is a very generalized idea about the length of your vector. Okay. And so length of your vector should be greater or equal to 0. And if you have 0 vector, then the length is 0. And then you also need to have linearity. So if you multiply your vector by some scalar alpha, so you have twice of your vector is stretched twice, and then the norm should also become twice. And if you have -1, the norm is still the same. Okay. So if you multiply by alpha, then the norm can multiply by the absolute value of alpha. Okay. And also, then the third one, we have a weirder thing. Then the norm also needs to satisfy triangle inequality. And so yeah, so we have a triangle here. It says that you have a vector v and a vector w. then the length of v plus w should be less or equal to the length of v and the length of w. Okay, and yeah. So a vector space doesn't necessarily has a known, but if it's a known, then it's called a known vector space. And known vector space does not necessarily have inner product, but I guess if you have inner product, then it's a known space because you can define a known on inner product space. Okay. Yeah. So this is also the next theorem. So we want to say the inner product space, the known associated with inner product we have been talking about is actually a known that satisfies those three equations. Okay. And okay, and so that's the theorem, and we have proof. Okay. And okay, so 1 and 2 are kind of skip, but let's try to say that a little more. Okay, so one we have been talking about inner product is the first property of inner product, and 2 2 can be easily gotten from the linearity. Okay, yeah. So remember we have okay. So 2, I guess I can write here. So remember we have linearity on inner product. So alpha x plus beta y z equal to equal to alpha x inner product with z plus beta y inner product with z. And so if you just take beta equal to 0, then you see that alpha times x inner product z equal to alpha x z. And yeah, and then also by symmetry, then you also have x alpha z equal to alpha x z, right? So you have alpha x, and that's just alpha square xx. Okay, so that's 2, and okay, so 1 and 2 is easy, and we can check 3. So we want to check uv v plus w inner product is less equal to, sorry, v plus w known is less equal to v known plus w known. Okay, and well, know that it has a square root is a little annoying, so let's do the square version. Okay, so u plus, okay, so instead of v and w, we'll do u and v. But anyway, so u plus v known square, then as defined is u plus v inner product with u plus v inner product. Okay. And then we know it's linear on both arguments, and so we can do distributive rule. And so it's u inner product with u, v inner product with v, and with the closed term by symmetry, once again we have twice u inner product with v. Okay. And now we can use the Cauchy-Schwarz we just proved. Yeah. So we use the Cauchy-Schwarz we proved, then I guess we can, yeah, so we kind of skip one step. So we know that then this thing is less equal to the absolute value of this thing, right? So obviously you take absolute value, things only go up. Then you take absolute value, then you use the Cauchy-Schwarz, and you see that this is less equal to twice the u known, v known. Okay? So remember, yeah. So the Cauchy-Schwarz says the absolute value of this thing is less equal to u known, v known. Okay? And yeah. And then this is u known plus v known square. Okay, so we have u plus v known square less or equal to u known plus v known square. And we know both of those are positive, so you can just take a square root of both sides. And so you have u plus v known less than u known plus v known. Okay? Yeah. Okay, and okay, but now, okay, so inner product we say is very general, although we don't have too interesting example. But for knowns, we now actually have interesting example of different knowns. Okay, And yeah, so even in Rn, so now we're back to Rn, so it's a very familiar place. But even in Rn, we can divide very interesting known on them. Okay. And they actually use quite a lot. So we have a 1 known, 2 known, p known, infinity known. Okay. So they are all in the same series. So the usual known we have is actually called 2 known because it's a square of every element summing together, and then you take a square root. But you can also take, say, for example, 1 known. Okay. And that's just, you take an absolute value of each coordinate in your Rn and add them together. That's 1 known. And the 2 known is the usual known we talk about. So it's a square of every coordinate, then summing together and take a square root. And so these are actually special case of what we call p known. And that's just, you take absolute value of every element and take them to p's power, summing together, then take this p's root. Okay. So the p known is a very general idea, and you can even have p. So by definition here, you can even have p as a non-integer. I think p only needs to be positive number. Okay. And yeah, so for every positive number, you can divide the p known. And do we check? I guess we didn't check, but yeah. We didn't prove here, but you can check that those are actually knowns. So even you have this funny equation, they actually satisfy the triangle inequality. Okay. And yeah, so then a special case about p known that's a lot of time used is you take a p to infinity. And what happens is the largest element here will dominate because you take a very large power. And so that's just the maximum value of every one over the absolute value of the coordinate. Okay. And yeah, so basically the 1, 2, and infinity are the most you will see. Okay, the 2 known is the most common known, but then talk about p known, then 1, 2, and infinity are the known that sometimes you will see in research. Yeah. And yeah, and now back to the thing we talked about. So known is not necessarily correspond to inner product. Okay. So p known they only need to satisfy those 3 things. Okay. And the inner product structure is HR structure, and so for p not equal to 2 doesn't correspond to inner product, and they don't have the Pythagorean rule. Okay. So for example, we have those 2 vectors that are orthogonal. So x1 equal to 1, 2, x2 equal to minus 4, 2. Okay. And then we can calculate, and okay, and so they sum into this minus 3, 4. Okay. And now we can see the different known of those things. Okay. And so let's check the infinity known. Okay. So the infinity known of x1, as we say, is the maximum element of x1, then it's 2. And the infinity known of x2 is this 4. Okay. So x1 infinity known square plus x2 infinity known square is 20, and then you can check x1, x2 infinity known. You take in this 4 here, that's this 4, and the square equal to 16. So you see that, yeah, so infinity known don't satisfy the Pythagorean rule. Okay. Yeah, and also then, but you see that the 2 known satisfy the Pythagorean rule, as we say. So x1 known square is this 1 square plus 2 square, and x2 known square is this minus 4 square plus 2 square. So it's 5 plus 20 equals 25, and yeah, and x1 plus x2 square known square, 2 known square is also 25. Okay. So only 2 known satisfy Pythagorean rule. So for example, infinity known doesn't satisfy Pythagorean rule, and then you also don't have Cauchy Schwarz, etc. So you cannot define. Yeah, I guess you can try. No, yeah. So you cannot cannot really define the angle by the infinity norm. Okay. So you want the angle, then you need the inner product structure. Okay. And yeah, so here is an example of some knowns in a vector. So x equal to 4 minus 5, 3. Then one known is the absolute value of each coordinate adding together. So just 4 plus minus 5 plus 3, then equal to 12. And the two known is everything squared and taking square root is 5 square root 2. And the infinity known is just large number, it's 5. Then you see they are all different. Okay. But but somehow they still provide a distance measure between vectors. Okay. And yeah, so distance between vectors is just the difference between two vectors and take the known like you like. Okay. And another example of known. So basically the two known Rn and well, we already defined inner product, so we can have the nice known that associated with inner product Rn by n. Okay, so it's just this element-wise inner product and then taking square root. And this is famous. I'm not sure. Maybe we'll talk about it later. But this is called the forbidden known. Okay. And so this is element-wise two known of the vectors. Okay. But forbidden known has a very nice property that we might see later in eigenvalues. Okay. But yeah, so we can also define known matrices and just element-wise inner product and then take the square root. Okay. And yeah, so we can see the inner product between two matrices. So we have actually we have this example earlier. Oh, I see. So anyway, so we see you have two matrix, then we have inner product, then we just multiply the element by element together. So 1 times minus 1, 1 times 1. Those element-wise product, then summing them together, then you have this inner product between the b equal to 6. And then we have forbidden known of A is just the sum of elements squared, then taking square root. And forbidden known of B is sum of element, then taking square root. Okay. And any question? Yeah. And yeah, so that's a checklist of everything. So definition of inner product, and so definition of inner product need to satisfy those three things. And so inner product is greater or equal to 0, and equal to 0 if only if x equals 0. Then it's symmetric between two arguments, and it's linear on the first argument. And then we have then from inner product we can define a whole bunch of geometry. So we can define length as the square root of the inner product. And orthogonal, if inner product is 0, then we can define projection. And if coadjutors, then we can define angle from the inner product. And then we have even more general definition, that's a known. Okay. So yeah, so known is some operation on every vector. I guess not operation, some function on every vector that maps to a real number, and they need to satisfy those three properties. So and then we check that the known divided by inner product is actually a known, and but there are other known like L1 known, L2 known, and infinite known Rn. And then there is forbidden known for matrices. So forbidden known for matrices is easy to define, but it's mostly about the name you need to remember. Okay. And yeah. So any question? I guess the one thing I can say is forbidden known for matrix, because you see it's a square here, and sometimes it's also called two known matrices, but it's a little complicated because there are a lot of ways to define two known matrices. Okay. So sometimes it's also called two known, but this is a little ambiguous. Okay. There are a lot of matrix knowns you can define. Okay, and I think that's it for today. So no question, then let's meet again on Monday.